the n vector space. The set of all n vectors of a field F is called n vector space over F and is denoted by Vn of F, or in short, if the field is clear, then just as Vn. So if A is equal to A1, A2 and so on up to An is a non-zero vector of Vn, then the set S of vectors Ka is a subspace of Vn, where K is a variable which can take any value. So here you have a vector A which is a non-zero vector, and when we multiply it with a variable scalar and we map it to a coordinate system, then what is covered is called the subspace of Vn. Okay, a vector space which arises as a set of all linear combinations of any given set of vectors, we can say spans the given set of vectors. In other words, the set of linear combinations of vectors having same number of components called the span of vectors. Okay, so span, a vector space, a subspace, and now we have the basis of a subspace. So a set of vectors A1, A2, A3, AK belonging to the subspace S is called the basis of S. If two conditions have to be satisfied, the subspace S is spanned by the set A1, A2 and so on up to AK, and the second condition is the vectors are linearly independent, right? So the number of members of the basis set is called the dimension of the subspace. Yes, so now that we have this, we can look at row space. If we represent each row as a vector, then the vector space formed by the set of linear combinations of all those vectors will be called the row space. Okay, so we have seen row space and we have also seen basis of a subspace. Now let's look at the row rank of a matrix. Let A is equal to Aij of order m by n. Each row or m rows of A contains n elements. Therefore, each row is a n vector. Now, the set of all the row vectors spans a subspace R of Vn. This subspace is called the row space of A. Now, the dimension R of capital R is called the row rank of the matrix. That is, row rank of a matrix is equal to the max number of linearly independent rows of A. So we have looked at row rank of a matrix. Now column rank of a matrix. So let A is equal to Aij m by n order. Now here each column of A contains m elements. Yes. So therefore we can say each column is a m vector. Now the set of all the column vectors spans a subspace C of Vn, or in this case Vm, and is called the column space of matrix A. Now the dimension C of C is called the column rank of the matrix A. That is, column rank of a matrix is equal to the max number of linearly independent columns of A. So we have seen vector space, we have seen subspace, we have seen span of vectors, we have seen basis of a subspace, we have seen a row space, we have seen a row rank, we have seen column space, column rank. Now let's look at something called as nullity of a matrix. Okay, so let A is equal to Aij, which is a m by n matrix. So you have m number of n vectors, and let's say we have another matrix Bij, which is a k by m order matrix. So which means k number of m vectors. So here Ax is not defined. Xa is defined just by looking at this. So then the subspace S of Vm generated by the row vectors x belonging to Vm such that Xa is equal to 0 is called the row null space of the matrix AK. The dimension S of the subspace is called the left nullity of A. Why left nullity? Because it is being pre-multiplied. So what does this basically boil down to is that the row rank plus the row nullity will give you the number of rows of the matrix, or we can say R plus S is equal to M. So you might be wondering, if there is something called as left nullity, there must be a right nullity also. Yes, so let's look at that. So let A is equal to Aij, which is a m by n matrix, and Y is equal to Bij, which is a n by k matrix. Now let's say here uh, this is written as a column vector, not as a row vectors. Now in that case, what happens? Ya is not defined, yes, whereas ay is defined, n by k ay. So m by n, n by k. So ay is defined. So now subspace T of Vn generated by the column vectors y belonging to Vn such that Ay is equal to 0 is called the column null space or column nullity of A. So which means the column rank plus column nullity is equal to the number of columns of A. So now the null space. If we take a set of all possible solution vectors of Ax equal to 0, then vector space formed out of that set is called null space. In other words, null space contains all possible solutions of a given system of linear equations, always including the zero vector. Okay, so that's it for now. Bye.